The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. This is Julie Bloomquist. I'm with the DBA Virtual Chapter. Today we're going to have a lecture from Joey D'Antoni talking about in-memory column store indexes and how to make your data warehouse fly. This is being sponsored by Dell. And Dell Software does sponsor this meeting and comes up with the money so that we could have our raffle drawing. We are part of PASS. Please sign up for a free membership today at thesqlpass.org. Here is a listing of all the SQL Pass virtual chapters. They give lectures throughout the months. You can go to the PASS website and choose to become a member to the different virtual chapters, get the email notifications for their meetings. PASS does have an outstanding volunteer program. If you know anybody who would like to recognize as an outstanding volunteer, please send in a nomination. The PASS Business Analytics Conference is coming up May 7th to the 9th in San Jose, California. There are still discounts available for registering. Please come join us for the Business Analytics Conference. So Joseph or Joey D'Antoni, he's an architect with over a decade of experience working in both Fortune 500 and smaller firms. He's currently a solutions architect for the SQL Server and Big Data for Enhancements in Pennsylvania, Pennsylvania.
Outside of Philadelphia.
Correct. He holds a BS in Computer Information Systems from Louisiana Tech University, which I'm guessing is someplace with warmer weather, and an MBA. Oh, really? And an MBA from North Carolina State University. Joey's the Vice President of the Philadelphia SQL Server User Group and a member of the board of the PASS SQL Oracle and Healthcare virtual chapters. He's a frequent speaker at the local user groups and code camps and, of course, the SQL Saturday events. So I'm going to staff. Okay, so I'm just going to make you the presenter, change presenter. Let's see if I get your right one, Joey.
Wrong one.
Wrong one, okay.
Perfect. I may have to kill this other invite. No, here we go. Okay.
Did you get it?
Yeah, I got it. Let me get the right screen.
Whoops. I have the slide deck, but it's small.
Yeah. Yeah, hang on. I'm not seeing the my option to, here we go. Okay, boom. You should see Management Studio.
Yes, and now I see the big slide.
Okay, cool. Hi, everyone, and welcome. Today we're going to be talking about in-memory column store indexes, making your data warehouse fly. I'm Joey D'Antoni, like Julie mentioned. We had a couple polls before as people were waiting, and about 43% of you hadn't heard of the feature column store indexes. We're going to talk today about column store indexes in SQL Server both 2012 and 2014. This feature was introduced in 2012, but it's got some great enhancements in 2014. Like Julie mentioned, I work at Enhancements. We're a Microsoft Gold partner. I speak a lot about DBA stuff, big data, and career management. My Twitter handle is jdanton. I'm on Facebook and LinkedIn. If you want to reach me, Twitter is a really good way to do it. I can answer any questions there or during this session. So today's agenda, we're going to talk about indexes, a basic overview. I know most of you are DBAs, so a lot of this is going to be elementary, but we're going to talk about, Columnstore and, clustered versus non-clustered indexes and kind of how that works, because there's some caveats with Columnstore indexes. Then we're going to introduce Columnstore indexes. And Columnstore indexes are the official name is X-Velocity Memory Optimized Columnstore Indexes, because this is part of the X-Velocity suite that Microsoft purchased a couple years ago. It groups and stores data in a columnar fashion as opposed to a traditional row format of a data. For some types of queries, the query processor in SQL Server can take advantage of this column store layout to significantly improve execution times. The big place we're going to use these is data warehouses, and we'll explain why later. But basically, when we get to larger and larger sets of data, like terabyte plus, this feature really comes through and shines. We use memory more efficiently. We just do a whole lot of things. But the most common use cases are common data warehouses queries, such as filtering, aggregating data, grouping, and star join type queries. We'll do a little query performance demo. So we'll compare a clustered index against a traditional clustered index against a column store index. We'll talk about 2012 and 2014. There's some pretty big changes in the space with column store indexes, the biggest one being able to update them, but there are some other changes. Then we'll kind of walk through a 2014 demo, and we'll take questions at the end, but additionally I'll take questions. There's a spot where we stop talking about 2012 for a second, and I'll break for questions there. One other thing to note, because I know this stinks when you come through a presentation and it's not something you can use. Column store indexes are an Enterprise Edition only feature. Like I said, it was introduced in 2012. So if you have SQL Server 2012 or 2014, which isn't live yet, you can use column store indexes. But Enterprise Edition only, sorry. So indexes, we all know and love indexes. They make our data access very fast. The main purpose of an index is to speed data retrieval, and we're retrieving an extra copy of data. So, for example, in this picture here, I have the Dubai city map, and this is an index to the map. It's really a simple index. It's almost like a primary key index where we have the number 1 and then the location. So those numbers are going to show up on the map. So instead of having to read the entire map to look for where, for example, number 2 Albada is, when we see the number 2, we know it's Albada. The query optimizer works the same way. SQL Server allows us to use filtered indexes. Those can be really good, particularly if you have a weird cardinality skew in your data where you have a large percent of values. For example, in this data, it appears that we have a large percent of values that begin with A relative to the total data. So we might want to create an index just on those A's to faster speed data. It can be function-based, and it can be ordered. The penalty to using indexes is twofold. Writes become more expensive, so whenever we're writing to our table data on an insert or an update, we also have to write to our index or multiple indexes. So then we can have multiple indexes on a table, so we can always write, and that's going to be our penalty, is that writes, for each index we have an additional write when we write data. Additionally, more storage is going to be required because we have to store those indexes. So like anything else in database performance, everything's kind of a trade-off. So indexes in SQL Server. The traditional 2 indexes are clustered and non-clustered indexes. And clustered, I talk a lot about high availability and disaster recovery. Clustered indexes have nothing to do with SQL Server failover clusters. That's a pretty common SQL interview question. I like to use the term index organized table, even though I'm stealing it from another relational database management system. I think it's a little clearer than clustered index. Basically, your clustered index is a copy of those pages of data. Not a copy, it's the pages of data in the table in an ordered fashion. A non-clustered index is just an index, as I call it. So it's a very basic duplicate set of data. And the reason why I'm talking about this clustered and non-clustered index thing, and we'll reiterate this a few times, in SQL 2012, a column store index, which is where we're going to get to eventually, can only be non-clustered. What that means is that it's going to be a duplicate copy of the data. When we're talking about, it is compressed, so we do get space savings, but we're talking about large warehouse tables that can be really inefficient to have a full second copy of our data set. With a clustered index, it's the same data as the table. So basically, if we build a Columnstore index, and you'll see the syntax for that's rather interesting, that's clustered in SQL Server 2014. We only have one copy of our data. We're not paying an additional penalty to store 2 copies. The classic example of a clustered index is a phone book. The data is ordered as it's inserted into the pages. And clustered indexes sort and store the data rows in a table or view based on their key values. And these are the columns that are included in the index definition. There can only ever be one clustered index in the table because the data rows themselves can only be sorted in one order. The only time the data rows are stored in a table or stored in sorted order is when the table contains a clustered index. When a table is called a clustered index, it's called a clustered table. And if a table is has no clustered index, the data rows are stored in an unordered structure called a heap. These things are neither good or bad. It's generally a good idea to have a clustered index on all tables, but there are some exceptions. There are some times where a heap may perform better. One thing to note, if you're using Windows Azure SQL Database, all of your tables require a clustered index. I think Microsoft there was trying to protect from runaway I/O. So a non-clustered index is basically just a duplicate copy of a subset of the data in the table. Generally, they're created to improve the performance of frequently used queries not covered by the clustered index, or to locate rows in a table without a clustered index or a heap. We can, like we mentioned, we can create multiple non-clustered indexes on a table or index view. And this is fairly common, particularly in a data warehouse environment, where you have multiple different types of queries that you may create multiple either function-based indexes or multiple non-clustered indexes on a table. So why all this talk about indexes? Indexes make our stuff go fast. I'm a big fan of the NFL, the National Football League in the U.S., particularly the New Orleans Saints, which is where I'm from originally. And traditional indexes are stored in rows, much like my seats in the Superdome, and that picture is pointing to my section. When a query utilizes an index, the index is read row by row, much like I walk up the stairs to my seats in row 20, section 110, seat 610, seats 8 and 9, to see the Saints play. For those of you who are in Seattle, I think you guys are going to beat us this weekend, but go Saints. The columns on the right kind of represent our query against a Columnstore index. And those columns are Corinthian columns. I looked that up because that was a trivia question I got recently. Instead of returning rows, the query initially returns columns. It returns columns in segments, and we'll talk a little bit about that later. It's not exactly, so we do eventually get to rows, but it's a more efficient process. One interesting thing to note, when we query against a Columnstore index, the query only pulls back the columns that it's looking for. So if we had 5 columns in our table, and we only had 2 columns in our query, we're only going to pull back those 2 columns, whereas opposed to the row-based traditional B-tree index, we're going to go through each of those rows and all of that data that we didn't need to go through to return the results of that query. So let's talk about data warehouse queries. Data warehouses tend to be our largest environments by data, unless you're running some sort of big data environment that has a 100-node cluster or something. But in the relational world, data warehouses tend to be our largest environments. They have a lot of data. We know that querying lots of data can take a really long time, particularly because when you start talking about databases, are the ways we make things faster by utilizing memory better, because memory tends to be a lot faster than disk before we go to an all-solid-state paradigm. But even then, memory is still faster. Data warehouses are large enough that we can store all of our query results in memory. There are some techniques like Fast Track Data Warehouse from Microsoft that we can use to improve the performance, but a lot of times the bottleneck is still at our storage subsystem just because we're reading so much data. And we're processing data row by row. For something like an aggregation, that might not be the most efficient way to do it from a purely computer science perspective. columnar formats are really good for these sort of things. The traditional approaches we've taken to improving database performance in data warehouses are to partition our tables, typically by date. That's the most common scenario. We create index rows, so for index views, sorry. So an index view is typically used when you have a complex aggregation of data that you want to persist. So an index view, for those of you who don't know, is a view that's basically persisted to disk, and we build a clustered index on it so we can return our results that much faster. And then data compression. Data compression is kind of like a read performance turbocharger for SQL Server. In a nutshell, you're reading less data since you're compressing. The reason why compression got introduced was CPUs started getting more powerful, and CPU stopped being our limiting factor in data warehouses, and disk speed did. So we could give up the CPU cycles to decompress the data as we read it to reduce the I/O reads by reading compressed data. A couple of these things still apply in this new Columnstore format we're going to talk about in the next slide. Partitioning is still a very valid function. And we're not going to use data compression in the traditional SQL Server method of using data compression, but Columnstore indexes are a form of compression. And actually, if we look in, for example, sys.partitions, which shows whether or not a partition is compressed, you'll see a number and a type of compression for Columnstore compression. So SQL Server's engine views it as a form of data compression. So in SQL 2012, we got this cool new feature called Columnstore indexes. Data is stored in columns as opposed to rows. And this allows for a much higher rate of compression than we might traditionally get with page or row compression. I use this example once again, we go back to the phone book. But here we see this data stored in columns instead of a traditional phone book. We have all these people named with the last name of Disney. We could replace all of those with one Disney and a pointer. And similarly with the phone numbers, we could get a great deal of compression since the data in columns is more likely to be aligned than data in rows. So we're going to get a great deal of compression, and we'll see that in the demo. Like I mentioned before, if we're not using a column in a query, it's not scanned or returned. And for that reason, the recommended practice is to add most columns, if not all, in a table to your Columnstore index. Typically, you're going to add all of them because there's no penalty to it. There is in SQL 2012, we have the storage penalty, but when we get to SQL 2014 and we can make a Columnstore index a clustered index, then there's really no penalty at all unless you run into some of the data type limitations that we'll talk about in a few slides. So columnar storage. Columnstore indexes in SQL Server use this patented technology from Microsoft called VertiPack. And for those of you who are working in the BI space, this is a lot of what's behind Power Pivot and some of the compression techniques used in analysis services. SQL Server Columnstore indexes don't have to fit into the main memory of SQL Server, but they can effectively use as much memory as available on the server. Traditionally, we'd use rows and store those on pages. In the Columnstore, we're storing what's known as row groups in column segments. So let me highlight this on the screen a little bit. Here we have these row groups and column segments, and its data is stored in those formats. These are actually stored as lobs in the database, and we'll take a look at that in the demo, which I promise is coming next. So even though we can't compress lobs in SQL Server, this really compressed index format is storing as lobs. So let's go ahead and get into a demo. Switch over to duplicate. Okay, everybody can see my screen, it looks like. So we're going to use AdventureWorks 2012, and you'll note we're in SQL Server 2012, 11.003, so this is Service Pack 1. I forget what CU level I'm on here.
I'm just still seeing the slide deck.
Okay. Hang on, let me make sure.
That's good.
Okay. So there's two ways we can create a column store index. The obvious one is the basic syntax in T-SQL. It's basic create non-clustered, and we just add this keyword, column store index. The other way is through Object Explorer. And I'm going to create one on this really small table here. New index, and we have the option to create a non-clustered column store index. Same as any other index, we add our columns. I'm not going to go through with creating this because I think it's got unsupported data types. So let's take a look at this query. And this is kind of a typical data warehouse query. I'm using AdventureWorks here, but I'm using a script that Adam Mechanic wrote to blow up a couple of tables. And here we have a query that's doing an aggregation, so we're selecting transaction date and average quantity and average actual cost on a given day, or for a date range. So this query ran pretty efficiently. It was 2 seconds, but let's look at our logical read count here. We did 132,000 logical reads against that clustered index. Our execution plan was just an index scan, and as we see here, our execution mode was row. What row execution mode means is that SQL Server is analyzing that data row by row. So that's actually a pretty acceptable performance. My solid-state drive runs pretty fast, but in a real data set, we're going to be a little slower. If I run the same query with a column store index, and let's note we had 132,000 logical reads there. Let's see what we do against the column store. So we returned the same query, except this time we ran it sub-second. It ran in 10 milliseconds. And we had 50,000 logical reads. So we had over half the number of logical reads. And so where's the magic here? We see this batch execution mode. We'll talk a little bit more about that when we get back to the slide deck. But basically this means SQL Server is processing our data at 1,000 rows at a time. This is happening at a higher CPU cost slightly, but the I/O cost is so much lower, it works itself out on most modern servers. And here what we'll do is show our buffer utilization. This is a little procedure I have that shows how much memory is used by a given index. Unfortunately, since that my column store table is a heap and doesn't have a clustered index, it's stored in memory as well. But from the same query, I'm using about half as much RAM as I am for this clustered index table. That just shows the compression level we're getting in the clustered, non-clustered column store index. So you try to update a column store index. Let's see what happens. Update statement failed because data cannot be updated in a table with a column store index. Consider disabling the column store index after. Not really a great solution. We'll walk through that in a second. I wanted to show you guys one more thing that I kind of have out of order here. For our object ID here, and this is our column store object, you'll see this lob page count, lob use page count in sys.partitions. All that's saying is we have our data is stored as lobs in the partition. So it's kind of interesting that we're using lobs for that, but it works, and Microsoft did some pretty neat things. So we have two options for how we can update data in a column store index. And one of them is really simple and one of them is a little more complex, so we're going to walk through both of them. Here we're going to create a table and then just insert some data into the table, pretty basic, and then create a non-clustered column store index on the table, and then try to insert some more data. That's going to fail. We can disable the index, and if I go back and insert more data in, it works. And then we have to do a rebuild of the index. That works really cool for this demo where we have 2 rows. When we start talking about multi-million row data warehouse tables, not as good of a model. Building these column store indexes is going to be much like turning on data compression on a large table. It's going to be a pretty expensive process from a CPU perspective because it's compressing particularly hard. Our other option is to add data to a partition table with a column store index using partitioned switching operations. Don't worry if you don't get this in the demo. I have a PowerPoint slide that will explain it a little better. But we're going to go ahead and create a couple of tables here. So we're creating a fact table and a staging table. And then we're going to create a partition scheme on this table. Our partition function and partition scheme for the table. So we're partitioning our table here on our date key. And now we're going to add some data, and the key thing is that we're going to leave an empty partition on the end. So we insert our data, and after we've done our initial data load at the beginning, and we have our empty partition, we're going to create a non-clustered column store index on the table. And it's aligned to the partition scheme. So here we'll show the data and the partition number. And then we're going to split the uppermost partition. This is a metadata operation, so it's really fast. Now what we're going to do is create a staging table where we're going to do our incremental data loads. So we did our initial load into our fact table, and we're going to create this staging table where we're going to do our incremental loads. Put a constraint on it so it's got the same partition bounds as the newly created partition that we have for our fact table. And then we're going to insert data into it. After we've done this would be our incremental data load. So this would be like our nightly ETL job that we might do in an SSIS package, for example. Here we're going to create our non-clustered column store indexes on that staging table. So we're finished doing our insert. And what we're going to do here is switch our partition to our fact table. No errors. And then we can retrieve all our rows from the fact table, which was our second row that we added. So that's a very nice, elegant way to do it. It's not as straightforward as I'd like, but it's functional. So Julie, do we have any questions at this point? I felt like this would be a good time to take a few. Julie?
No, I don't see any questions.
Okay, I'll keep. Okay, cool. So how is Columnstore so much faster? A couple of things. It's a very good compression ratio for column-oriented data. We get better utilization of memory. As we saw, we had about half as much memory utilization from the column store index as we did our clustered index. The segment elimination process can skip very large chunks of data. And most importantly, according to the white papers from Microsoft, is batch mode. We process data in chunks of 1,000 row batches rather than row by row. And SQL Server sees a 7 to 40 times CPU savings by doing that. The key to getting the best performance is to make sure your warehouse queries are largely in batch mode, and that's a quote from Books Online in regards to this feature. So batch mode's a huge deal, and like we showed, we see it in our actual and estimated execution plan. In Books Online, and I have this. If we go to, I have a blog post on this, and I'll have that in resources at the end of this with some links. Not all query operator types are supported in batch mode in 2012. More are supported in 2014. So we'll kind of walk through that, or I'll give you the resources to see that after. So why don't we column store everything? We have all this awesome performance. What's the negative? We can't update and insert in 2012. That's by far the biggest challenge. that update process I just showed you guys, I don't think it's too terrible, especially if it's integrated into a daily process. But some people think, you know, partition switching is a relatively advanced thing. Not everybody's going to be doing that. Can only be a non-clustered index, so we're storing a lot more data on disk than we ordinarily would be. Although probably not that much more because we have a lot of other non-clustered indexes. Our data types are somewhat limited. So, for example, in 2012, and I haven't fully tested this in 2014 to see what's allowed now, because there's a white paper that Microsoft wrote on the 2014 version of Columnstore that's linked in my blog post that mentions that some of the data type restrictions are going away. They hadn't changed at all in CTP1, but I presume they've changed some in CTP2 of 2014. The following types can't be used in 2012, though. Decimal or numeric with precision greater than 18, binary, var binary, image, text, varchar max, in varchar max, cursor hierarchy, unique identifier, so no GUIDs, SQL variant, and XML. What most of those data types have in common is that they don't compress really well, so the attempt to compress them would be probably really expensive from a CPU perspective. That's kind of the big thing. We can only have one index per table. I don't think that's a limitation. Given the way they're used, we can just add all the columns from the table into them. And then lastly, it can't be a sorted index, which once again, I don't think is necessarily a huge showstopper, given the nature of how column store indexes work. So this is the process you just saw. This is I didn't bother to show the dropping the index and rebuilding it or disabling and rebuilding it because that's pretty obvious. But here we have our fact table, and we built a column store index on it, and we had our initial load. And here we have data to be loaded, and that's going to go into our staging table. After that data is loaded, we're going to build a column store index on it. Additionally, we're going to add empty partition into our data. Now, the data in the staging table has to be aligned to the data in the fact table partition, but not a big deal. And then from there, we're going to do a partition switch from the staging table into the fact table. This is a metadata operation. Partition switches are extremely fast. So we're only doing effectively a single data load and then a metadata operation to switch that data into the partition, as well as the column store index build on that staging data. So where do we use our column store indexes? We should use every column in the table in the column store index. If you don't, then a query that references a column not included in the index will not benefit from it much or at all. We should only use them on really large tables. The official Microsoft recommendation is fact tables and dimension, all fact tables and dimension tables that are greater than 3 million rows. One of the interesting things from a data warehouse perspective, I was playing with the Contoso retail data warehouse recently. And some of the, there's a big analysis services cube that's built on top of it. And one of my BI architects here asked me, you know, what kind of performance impact would that have? And the answer was, it turned out that the cube processing time, once I included column store indexes on all the fact tables and the Contoso BI data warehouse, it took the cube processing time on my laptop, which admittedly is pretty fast. It took it down from 3.5 minutes to about 1:40. So it was a pretty incredible performance gain. I think that probably relates to CPU and I/O in that scenario. And we should structure the queries that we're hitting our warehouse against as star joins with grouping and aggregation as much as possible. Microsoft recommends against joining pairs of very large tables. So if we can join a very large fact table to one or more smaller dimensions using standard inner joins, that's really good. And from a data modeling perspective, it's pretty traditional data warehouse where we use dimensional modeling as much as possible to structure our queries that way. And additionally, we should use best practices for statistic management and query design. And it's kind of, that's independent of column store technology, so we should make sure our statistics are up to date. One interesting thing is due to the blob storage mechanism, fragmentation is much less of an issue. It becomes a little bit of an issue in 2014, but I don't think it'll be a tremendous issue. So I don't think we're going to be rebuilding these indexes all the time like we otherwise would. In I'll get these slides posted to the deck, but this article here is Microsoft's guidance on Columnstore performance tuning. So if you click through, you'll get to see a pretty good answer. So Columnstore 2014, I call this the Holy Grail, or this is a picture of the Holy Grail. It's not exactly the Holy Grail. It's really cool, though. We're not going to be using these for everything as much as I'd like to, but they get a lot better. What do we get in 2014? Fewer data type limitations. Like I mentioned, that's according to a white paper from Microsoft. I need to test that out in greater detail. Our Columnstore index becomes updatable, and therefore we can insert new data into it as well. It can be a clustered index, so we don't have to store 2 copies of data on disk, so we can really get benefits of those compression gains that we're going to see. We get a new archival compression mode, and we'll see this in the 2014 demo. I used to work in healthcare, and I had a lot of systems that were written by third-party vendors that didn't have an archive tool built in, so we had to keep all our live data in the database for however long our legal requirements were. And if any of you have worked in healthcare, you know those legal requirements can be pretty incredible. So there can be a great deal of legal time. Some of the things in pharma and healthcare we had to keep for 20 and 35 years, and we had no archival mechanism. This is where this archival compression mode would come in. You'd want to use this, and we'll take a look at it and see the compression gains we get. But you'd want to use this where you have a clustered index, a clustered Columnstore index on a partition table, and you have lots of partitions that are basically dead to the world and never read. Microsoft's saying we'll get 25 to 30% additional compression on this. I have a blog post on it that shows some details around what I got in testing. That appears to be accurate to me. The one thing, it's compressed so much that the CPU time it's going to take to uncompress this data is actually longer than it's going to slow down your query performance. So you really only want to do this on data that you're not hitting a lot. Additionally, we talked about batch mode, how not all the query operators were included in it. This gets better in 2014. It's, once again, I know I keep referring to this white paper, but it's detailed there. So the Columnstore update process. This is a pretty interesting process. We've talked a lot about compression and how deeply compressed Columnstore indexes are. Given that compression is a very CPU-intensive operation, so if we go to build a large Columnstore index, we're going to see very large CPU hits. Microsoft had to, and almost everybody else who's doing this had to do it asynchronously. There are several columnar solutions. HBase, which is part of the Hadoop stack. Oracle has something, but they require you to buy their own hardware called the hybrid columnar compression. And HP has a product called Vertica that's very similar. And they all do their updates in a very similar fashion. Basically, updates to the index get written into a B-tree structure called the delta store. It's basically a table on disk, or an index on disk. They're collected there until they reach 1,000 rows. And then a process known as a tuple mover comes along and moves them into the index. We'll take a look at how you can see that in the demo as well. Bulk inserts, however, go through a special API. Bulk insert performance is critical because it's the bread and butter of data warehousing ETL scenarios. You're going to have to give attention to your pipeline and drive to achieve the optimal compressed format. So Microsoft built a special API for this bulk insert, but it requires the bulk insert to be able to upload close to 1 million rows partition in each, 1 million rows per partition in each batch. If your bulk insert is using too small of batches, then the result will be suboptimal delta stores. If you're using SSIS, you really have to pay attention to the buffer, to the data flow buffer size. Is the default 10 megabyte buffer in SSIS. It's just too small for achieving efficient Columnstore bulk inserts. And there will be cases where there just simply isn't enough data to upload. So the bulk insert will result in a delta store instead of a compressed Columnstore. Those delta stores will be left open, and subsequent bulk insert operations will reuse them and fill them up. The bad thing about the delta store is it's a B-tree, so you're not using all of your Columnstore. So it's going to be less. It's going to perform not as well. Having a little issue talking there. So let's take a look in 2014. So here, this is SQL Server 2014. And the first thing we're going to do is take a look at the syntax to build a non-clustered column store index, or a clustered column store index, I'm sorry. I'm going to go through the GUI first because I find this really interesting. It freaked me out the first time I went to do it. So just so you know, indexes, new index. We have the option to create a clustered column store index here. And actually, this was a bad table to do it on. Hang on. Another one. Basically, there's no option here to add columns, which really scared me at first. The syntax is simply create clustered column store index name on table name. That's it. So by default, if you create a clustered column store index, it's going to have all of the columns in it. And here I'm going to go ahead and create one. This isn't a huge table, so it should go pretty fast. And then we're going to look at our CPU. This is a VM, and this is a relatively small table. It's 25,000 rows. You can see that CPU spike. I didn't want to bore you guys with looking at Task Manager for too long. The other table I'm working on has 25 million rows, and it takes about a minute or two to build the index. And our CPU is pegged that entire time doing the compression. So here we're going to take a look at, we're going to update the table. This table has a column store index on it, big product CS, similar to the one you saw before. And we're changing our start and cell start dates. So that affected about 10,000 rows. And if I go to this DMV, which is sys.columnstore.rowgroups, and there are a number of DMVs around this. I have some of them blogged, others I have in the pipeline because I've been kind of interested in the internals of this. We see this state description open. This is our object. And I have where state equals 1, and that where state equals 1 means it's an open Delta store. If I just show my other row groups, we'll see that each of these row groups typically has about 1 million rows. That's usually SQL Server's aim for it. In this 3 state is that it's compressed already, so it's been compressed. But since we only loaded 10,000 rows, they haven't been processed into the Delta store. If we want to see what happens with that, and this process kind of happens asynchronously, we can go here to Extended Events. And I have this demo built called Columnstore Demo. And the things I'm looking for in this demo, by the way, if you haven't started working with Extended Events, I recommend watching Aaron Stelato's session from past. It's a very good intro. And this is going to be the replacement for Profiler. We have these 2 events, and they're debug events, so Microsoft probably doesn't want us looking at them, but the debug events are where all the fun stuff is anyway. We have this column store tuple mover begin, compressed, and incompressed. And this begins when the column store tuple mover compresses the data store. Like I mentioned, that's an asynchronous process. That update I did wasn't very big in terms of size. I haven't seen that fire with something that small. Typically when I've been updating a lot of data continuously, I see it fire. But it does fire asynchronously, and it does only want to fire when there's memory available to SQL Server. This is pretty much the way it works in Parallel Data Warehouse, is my understanding, which is where this feature was initially implemented. So it's an asynchronous process that happens. You see blips in your CPU utilization, and I have this blog. You'll see blips in your CPU, but it's not as dramatic as when we do a full build. So here I have a little stored procedure that's just going to show the partition space in this table I have called cluster column store load test. And this is going to show us the space used as well as the partitions. What we're going to do is rebuild our partitions with this column store archive mode. And much like any data compression technique, it's managed at the storage layer for the table through the GUI. So if we say manage compression, we have this default column store option, or we have archival column store. You'll only see that if you have a clustered column store index on a table. And actually what I'm going to do is run this quick query before we do this compression. I say quick, and it's going to go really slow for us here. Uh, 14 seconds, not too bad. So here we did 21,000 logical reads, so that's pretty good. Our execution plan, column store index scan. This was in row mode, interestingly enough. I'm not sure why it didn't get picked up for batch without investigating. We did 21,000 logical reads, and then we did 9,000 CPU seconds with an elapsed time of 13 seconds. So what we're going to do is alter and rebuild a lot of our partitions here with archival compression. And remember, we were looking at like 30 to 50 meg for each of our partitions. And I'm actually going to rebuild this whole table in archive mode, which we should never do this at home. Julie, this is going to take a minute. Do we have any questions?
Yes, we do. I was looking through them. So one question throughout is, why is it not ideal for a transactional database?
Basically, the update process is going to be a lot slower. The penalty for doing single row updates is pretty expensive, and if you're doing single row updates, they're going to all get written to the Delta store. So we're not going to really feel the benefit of using the column store index in the query. That's the biggest reason. Unless you're doing massive updates, the kind we're doing in the data warehouse, it's just not a very efficient process in a nutshell.
Okay, so here's one. I think he's just looking for verification. It says, so in a data warehouse where you would want to update a record within the column store index table, you would make a record in the non-column store index table and omit the record from the column store table somehow, making a copy of it and negating it from the column store index table.
I'm not clear as to if that's 2012 or 2014. In 2014, we simply do an update. In 2012, in terms of doing updates to existing data, there's no real easy solution to that. Typically, you're doing with a data warehouse, you're doing incremental loads. So you're going to see that's where that staging paradigm works well. If you needed to do an update, really the only solution I can think of there is to drop the index and rebuild it after your update cycle is done. Really, in a typical data warehouse architecture, you shouldn't really be doing updates against your fact tables anyway. But I can understand from time to time they need to happen. Anything else?
We're purchasing a parallel data warehouse. Is there a difference with the column store rules when using Parallel Data Warehouse 2012? SQL Server.
Good question. I am not trained in Parallel Data Warehouse. I haven't used it. My understanding, and the people you want to talk to are some of the folks at Pragmatic Works, like Jason Strayed or maybe Mark Stacy, who's not with Pragmatic. They're pretty expert in Parallel Data Warehouse. It's my understanding that the functionality is pretty much the same, but I can't speak to that directly.
And how about one more? What is the effect on performance when you join a normal clustered index column to a Columnstore index column in SQL?
There should be no direct impact. It's going to be more expensive to do that, to query the table that just has the clustered index. So our index build finished, or our index rebuild, our partition rebuild finished. And we're going to share the space we're using in archive mode. And as you can see, we're down. I believe this high one was 56. This is going to be like any other compression technology. It's going to be very dependent on your data. So how much further you can compress your data beyond Columnstore is just dependent on the data. And then we're going to run our same query. And it took about 13 seconds last time. Remember right, it was 9,000 CPU seconds. So let's see what it does this time. We have far less logical reads. I think we had 20,000 logical reads. And I should have copied my CPU time. So we do have less logical reads, but our execution time, actually in this case, it's about a wash. I have this pretty much detailed on my blog to show you how it works. But that archival column store compression is best used for data that you're not going to be reading frequently. That's all we have in the demo space here, so let's go ahead to the next slide. What do we do differently in SQL Server 2014? Best practices, in general, stay the same. I didn't see too much difference in how we're going to do best practices. Batch mode gets enhanced and gains more query types. The more query, when I say types, more query operators. So more types of joins and hash joins are supported. The nice thing is there's no need to worry about dropping and rebuilding indexes. We just append data. One of the things that's interesting is due to their nature, it's pretty hard for column store indexes to get fragmented. With the delta stores, however, since that's a B tree structure, conceivably that could be fragmented. So if you were doing a lot of update and delete activity, you could have some fragmentation in your B tree. I don't think there's a mechanism where you could rebuild those, though. So, and they theoretically shouldn't be open that long. You should be doing pretty large loads when possible. Still focus on your large tables where the data is not frequently updated. And archival compression is good for old unused data. Archive. I don't think we're going to be using this for OLTP. There was just a question about that. I didn't have it set up in the demo. If we had a little more time, I'd do it. Single row updates are pretty expensive still, and the model where it's really efficient is where we're doing bulk inserts and bulk updates. Even better inserts, because inserts are pretty straightforward. We're just writing to the data store and then appending it into the column store. With updates, we're doing an insert and delete operation. So the update operation is still pretty expensive. As great as this technology is, it's not really good for a transactional system just because of the sheer expense associated with that level of compression. And here I can take a few more questions if you have them, Julie.
Sorry, I have to keep muting and unmuting myself. Do you have any thoughts on how to handle inserts into tables with column store indexes with regards to late arriving data? We want minimal downtime, and I'm struggling to see a way around swapping the partition out of the table into a maintenance staging table, removing the column store index, inserting the data, creating the column store index, and swapping it back in. Just wondering if you had any thoughts regarding this. And obviously 2014 looks to solve this right off the bat with updatable column store.
Yeah, no, there's really, and that's really where the big limitation was in 2012. The partition switching process we kind of documented, or rebuilding the index, are really the only two. So to have late arriving data and I kind of have to be up all the time is a real challenge. All I can say is that if that's a business need and you're in one of those environments where your data volumes are so high, you definitely need to be using Columnstore indexes just for the performance gain. Think about switching to 2014 now. Microsoft is actually working with customers. You can go live on CTP2. There will be an upgrade path to the RTM version, and Microsoft is supporting it. As far as I know, contact your Microsoft, sales team on that. But as far as I know, you can run CTP2 live. They're comfortable with that.
Is it recommended that every column in a table is included in the Columnstore index? Would I include a column that is a unique key?
So yes, with a caveat. Every column should be included. If it has a unique key and you're using a GUID for your unique key, that's not supported in the index. I'm not sure if they supported it in 2014. I haven't tested it yet. But I know for sure it's not supported in 2012. If you're using a GUID, if you're using an integer unique key, which I hope you are, because I'm not a big fan of GUIDs, then yes, I'd include it. The cool thing about the way the optimizer treats Columnstore index, it only returns the columns that are in the query. So you're not really paying an additional penalty to keep extra columns in the index, like you would in a traditional view tree.
Right. So the next question was, why would you include all the columns in the same table into Columnstore indexes, and when would you not want to do that? So you're basically saying you're not giving a penalty for the index for the other columns.
Yeah. The only penalty you're really paying is, at least in 2012 with the non-clustered ones, is the storage on disk. But even then, your data is pretty compressed, so that's not that big of a deal. But yeah, the official Microsoft recommendation is to include all the columns if you can.
Do you have to check Columnstore indexes for fragmentations like the regular ones and rebuild or reorganize them?
No, less so, because they're stored as lobs. So, and especially in 2012, there's really no possibility for them to get fragmented because they're read-only. In 2014, like I mentioned, I could see a case where the Delta stores get fragmented, but you should be able to. You should be updating your data frequently enough that that's a non-issue.
And that seems to be all the questions.
All right, thanks everyone. Here's my contact info. You can email me at jdancon1@yahoo.com. My blog is jdantoni.wordpress.com. My Twitter handle is jdancon. And lastly, this is a link to my blog, but it's a blog post I have around this presentation called bit-ly/SQL Columnstore. And that's got slides and resources. So I've written a few blog posts on this topic. So they're all linked there. I have a link to the white paper from Microsoft, and I even have a link to some of the books online stuff from Microsoft regarding Columnstore indexes. So if you need some resources on this, or you just want to see the slides again, they're there. And this talk will be recorded, so if you want to see anything else, you can just go to the DBVC website and check it out. Thanks a lot, everyone, and have a good weekend.
Thank you, Joey. It was a great presentation. I also wanted to mention today that our raffle winner is Sergey Musafwamy, and he'll be receiving a $50 Amazon gift card courtesy of Dell Software. We'll be sending him an email shortly. Thank you again for attending.